The first talk is going to be by Kanishka Biswas. He is from JNCSR, Jawaharlal Nehru Center for Advanced Scientific Research, and he's going to talk on enhanced atomic ordering leads to ultra-high thermoelectric performances.
Yeah, so thank you, Didi, for this introduction. So at the outset, I'd like to thank Professor Anthony Cheetham for inviting me here. And also, I would like to thank His Highness for supporting this conference for many years and also supporting Sheikh Shakar Laboratory in JNCSR. So today, I'm going to talk how one can actually tune the atomic ordering or disordering to enhance the thermoelectric performance of a solid-state material. So let's start with a brief introduction of thermoelectricity. So thermoelectrics is a direct conversion of temperature difference to voltage. And that has been divided in two effects. One is Seebeck effect, which is discovered 200 years back. So in Seebeck effect, we have temperature difference, and this P and N-type semiconductors, or rather degenerate semiconductor, which are connected in electrical series, can generate voltage from this temperature difference. And this device geometry is that they are electrically series but thermally parallel. But in the case of Peltier effect, you can see we provide externally the voltage, and same device geometry, the same semiconductor actually can create temperature difference, and the cooling end can be used for refrigeration. And this has many uses over last 40 to 45 years. So what are the like why one should be interested in this field, thermoelectrics? Because you see, this is the pie chart for energy consumption in India as well as in world. So we consume energy in terms of combustion of coal, petroleum, and natural gas. Combustion of coal actually generates electricity, and combustion of petroleum and natural gas actually runs the transportation as well as industrial sector. So after use of enormous amount of energy in terms of this combustion process, we only use 35%, 30 to 35% of the energy. But you'll be surprising to know, basically, any energy conversion processes, like 60 to 65% goes out as a waste heat. So what do we do with this waste heat, right? So can we capture that some amount of waste heat and convert back to the useful form? So now, if you see this device geometry for Seebeck coefficient, and this hot end, can you use waste heat end? And this cold end can be room temperature or lower temperature from the waste heat end. So this semiconductor, what we actually synthesize in our lab, then they can convert this waste heat to electricity. So that's the broader motivation of doing research in thermoelectrics. And this technology does not emit any hazardous gas like CO or CO2. So that's why thermoelectrics is an important area of research. And you can see, in large scale, it can be used for power plants, where we day-to-day waste huge amount of energy as heat. So it can be used in chemical, thermal, nuclear, steel power plant. And medium scale, it has been already prototyped in different high-end cars, like BMW, Ford, GM, where the fuel efficiency of the car enhances when thermoelectric generator has been placed in the waste heat source in the car. So, and the other uses are basically for space power generation. So NASA, with collaboration with the Jet Propulsion Laboratory and Caltech, they have used this technology for their almost 30 to 35 missions for deep space mission, where solar cell may have much lesser intensity because or efficiency, because we have to go far from sun. So in that case, this radii sort of thermoelectric generator can be used for powering the electronics of the spacecraft. And new uses are coming, basically solar thermoelectrics, where we know all solar cell photovoltaics, where light part of the solar spectrum can be converted to electricity. What about the heat part? We have a lot of IR part of the solar, right? So, and then Shirley has given an excellent talk in battery, but all of you know, like, battery heats up. So thermoelectrics can go hand in hand with the battery technology to convert heat and make the system much more efficient. So basically, thermoelectric will not definitely solve all the problem, but it can go with the other energy conversion and storage technology to have a better energy management. And then I'm not going to talk about coolers today. So that are already used in many scientific instruments, semiconductor industry as a microprocessor cooling or spot cooling devices. So with this broader motivation, let's see what are the fundamental challenges in this field. So if you see, this is the thermoelectric figure of merit, and this is we made purposefully dimensionless. So one material can be compared with another material easily. And numerator of the ZT is having Seebeck coefficient, and Seebeck coefficient for students is nothing but how much voltage one material can generate unit temperature difference. That is basically delta V by delta T. And all of us know what is electrical conductivity, which directly relates to the carrier concentration and the mobility of the charge carrier. So the numerator of the ZT is basically the electronic property, which depends on electronic structure of the material. And the denominator of the ZT is basically thermal conductivity, how one solid material conduct heat from one end to another end of a solid. So it has two parts, which has electrical part of the thermal conductivity, where charge carrier actually carries the heat. And this is directly related to the electrical conductivity by IWAM and Franz law. So this is basically this electrical part of the thermal conductivity and electrical conductivity are actually related. And electrical conductivity and Seebeck coefficients are related by electronic structure and carrier concentration. But only independent parameter in this equation is basically lattice thermal conductivity, which I'll come in a minute, which is nothing but how lattice vibration or phonons carries the heat in a solid. So can we decrease this lattice thermal conductivity, or rather decrease this electrical thermal conductivity to have high ZT? So now, as a solid state chemist, we think the problem in a slightly different way. So the way we think, can we have material of a combination of metal, semiconductor, or glass? For example, like if you have metal, we'll have high electrical conductivity, semiconductor will have high Seebeck coefficient, and glass will have ultra low thermal conductivity. So thermoelectric material should have property of metal, semiconductor, and glass together. That's the challenge in this field, how one can make a, or one can make a new material which will have property of glass, metal, and semiconductor together. So that's the challenge chemists would like to take all the time. And more fundamental way to tell basically how we can actually decouple the electronic transport from the phonon transport. So can we decouple charge carrier in one sublattice and phonon in another sublattice? That is a more specific way to tell this problem. So with this introduction, so this is basically the how the lattice thermal conductivity actually acts. So the lattice vibration, which are quantized, which we call phonon, carries the heat, and which is the only independent part in the ZT equation. So, and you can see there are two types of phonon, optical phonon and the acoustic phonon. And acoustic phonons are generally responsible to carry the heat in a solid. And in a simple one-dimensional lattice, when the all atom vibrates in the same direction, it generates the acoustic phonon. And when the atom vibrates in a different direction, that generates optical phonon, which can be tracked by spectroscopic techniques such as Raman, IR, or terahertz. So this, how to slow down this acoustic phonon to decrease the thermal conductivity. And acoustic phonon are having the wavelength or mean free path in the range of 1 angstrom to 100 nanometer in a crystalline solid. So we have to block those acoustic phonon. So how one can do that? So over 50 to 60 years, people have tried many strategies to block the acoustic phonon. And the phonons, which carries the heat in a conventional thermoelectric material, are having the mean free path or wavelength in the range of 1 to 20 nanometer. So over the years, what people have tried, they have created microstructure, grain boundaries, but those scatters mesoscale phonons or micron scale phonon, which are not so important for carrying the heat in a solid. And people have tried solid solution or point defects. Those scatters the very, very short length scale phonon, which are having the mean free path in the angstrom. And those are also not very important to carry the heat in conventional thermoelectric materials such as selenides and tellurides. So people devised a mechanism where they put a nanoprecipitate in a solid matrix, and nanoprecipitates are the size of the mean free path of the acoustic phonon, which is actually 1 to 20 nanometer, and which scatters basically tremendously this acoustic phonon and decreases the thermal conductivity. The specific examples are, for example, this is, you see the lattice thermal conductivity versus temperature plot of champion material lead telluride in the field of thermoelectrics. And lead telluride thermal conductivity starts from 2.2 watt per meter Kelvin and goes down to around 1.1 watt per meter Kelvin at high temperature. So in 1960s, people have tried, or even slightly before that, making solid solution, lead tin telluride or lead telluride selenide. There is a decrease in thermal conductivity because we have this kind of point defects in the material. So that scatters some phonon and decrease the thermal conductivity, but it may not be in the glass limit. of that material. So then this paper came in Science in 2004 from Mercury Khanazzi's group. They actually put this nanoprecipitate, which is the similar size of the phonon mean free path in the late telluride matrix, and they could decrease the thermal conductivity almost near to the glass limit, which is around 0.5 watt per meter Kelvin. And later people have tried engineering the hierarchical nanomeso structure, putting nano point defects, nanostructures, as well as mesoscale grain boundary in a single material to decrease the thermal conductivity to the lower limit, and it could give rise to a ZT of first time above 2. So then, when I started my independent career in Bangalore, I understood the problem. This kind of nanostructure are very good to scatter the phonons, because they have the similar size of the phonon mean free path. But what about their boundary between nanoprecipitate and the matrix, right? So those are going to have defects and dislocation, and those are not good for carrier transport. So we always compromise with the electrical mobility of the charge carrier when we put this nanostructure. But this nanostructure are excellent to decrease the thermal conductivity, but we compromise of the numerator of the ZT. So can we devise a mechanism now, so which actually can have extremely low thermal conductivity, at the same time we have an enhancement in the electrical mobility. So that's the challenge remained for the field for many, many years. And we started working in that direction. And you can see that there is only one class of compound I'm going to talk today, because we work in different kind of compound, and we measure thermoelectricity in our lab of all this compound, but there is no time to talk all. So I'm going to talk about this 1562 class of compound, where one is sodium or copper or silver, 5 is basically antimony or bismuth, and 6 can be sulfur, selenium, or tellurium. So let us simplify the structure. So most of the compound in this class actually crystallizes in a basic solid-state chemistry structure, which is nothing but sodium chloride structure, which is interpenetrating face-centered cubic structure. I think all of us knows this. And I'm going to talk about only one compound from this series, which is AgSbTe2, where Ag and Sb are crystallographically disordered. They sit in the sodium position in an octahedral position, whereas tellurium sits in the chlorine position and form this sodium chloride structure. So, and this AgSbTe2 is not a new compound. We have not synthesized for the first time. It has been synthesized. It was synthesized long time ago, around 1970s, early 1970s. Where then people have done many experiments on this AgSbTe2, and experimental observation from crystallography as well as electron diffraction as well as high resolution TM, they showed that basically this silver and antimony actually disordered in the sodium lattice. And tellurium, of course, has a static lattice. So then we came across this paper from Bhanu Mohanty's group in Michigan State in PRL in 2007. He predicted first time basically Ag and Sb in this compound could be ordered, okay, and they can form like ordered structure, ordered superstructure, which will have slightly different symmetry compared to the rock salt structure. So now we wanted to have this ordered structure in our compound, and there is a particular reason why we wanted to have it, right? So disordering in a solid or disordering in a rather thermoelectric solid can actually scatter the charge carrier, which and that can limit the mean free path of the charge carrier. And in a non-interacting system, if the charge carrier mean free path matches the basically interatomic distances, the material electrical conductivity can go to the minima, which is called Mott Ioffe-Regel limit. Okay, so now if in a three-dimensional system, if we have a critical level of disorder in this solid, the system can become an insulator, which is called basically the Anderson insulator. The material can become metal to insulator. So now this is the electronic structure of a semi-metal. This is a cartoon of electronic structure of a semi-metal, because AgSbTe2 is a semi-metal. I'll show in a minute. You can see these are the localized states, which are basically Anderson localized states caused by disordering of atom. And this is the extended state where the Fermi level sits. Fermi level is nothing but the chemical potential. So now the extended states and the localized states are separated by mobility edge. And mobility edge concept has given by none other than Neville Mott. So you can see by tuning this mobility edge, one can actually tune the electrical conductivity and the Seebeck coefficients. How we can tune? So if we have more and more disorder in a solid, we can actually move this mobility edge towards the left side, inside the valence band or inside the conduction band, then the electrical conductivity decreases because it will have more electronic state localization and material may become an insulator when EC falls within the EF. So now, if you see the electronic structure, the Seebeck coefficient derived from electronic structure by the Mott formula, where S is directly proportional to the first derivative of the density of states at the Fermi level. So first derivative is nothing but the slope. So that means if you can distort the electronic state at the Fermi level, you can get a huge jump in the Seebeck coefficient. So then when EC, the mobility edge moves towards Fermi level, there is a distortion of the density of states from the normal parabolic energy dependence, and you can have increase in the Seebeck coefficient. So that means by tuning the mobility edge, by tuning the disorder of a solid, you can tune electrical conductivity and Seebeck coefficient at the same time. So that's the idea we have. That's why actually we wanted to play around with this, That's why we wanted to play around the disordering or ordering of Ag and Sb in this solid, or rather 1562 compound. So that's the broader idea we have, and we started working in this field. So can we order silver and antimony in this compound? So let's see how we can do it. And I should tell one thing, this Anderson localized regime is not so good for thermoelectric, because in the Anderson localized regime, electrical conductivity will vanish if EC moves towards EF, and it will become insulator, and Seebeck coefficient will assume a constant value controlled by the exponent of the electrical conductivity. So we have to work in a regime of weak disorder where coherent backscattering of the electron can have a partial localization of the electronic state. So we have to work in a partial localized regime, which is called nothing but weak localization regime. So that is good for thermoelectric. So can we achieve that regime in thermoelectric? So let's see how to do it. So then we try to understand why this Ag and Sb is actually disordered in this compound. So both sits in the octahedral position, and Ag plus has this Ag and Sb has a dissimilar size and charge. So there is a potential fluctuation of the lattice potential, and the compound actually become more and more disordered. So we have tried many ways to make them order. So what we have done over the years, and we zeroed down to this dopant cadmium 2+, which is exactly the average charge and average size of silver and antimony. Let's see, when we dope cadmium of this in this material, so then what happened? So in order to do that, what we have done, we have made the samples by normal solid-state seal tube reaction, and we get a very high-quality crystalline ingot of this AgSbTe2. And then we started doping of cadmium from 2 mole% to 4 to 6 to 8 mole% in this compound. So you can see pristine AgSbTe2 actually always have little bit of impurity of silver telluride. So because AgSbTe2 is a non-stoichiometric, slightly sits in the non-stoichiometrically in the phase diagram of Ag2Te and Sb2Te3. But as soon as we dope cadmium in this compound, this Ag2Te precipitate goes away, and at the 6 mole%, and then you can see there is a cadmium telluride precipitates come, which is tells that this cadmium actually breaks the solid solution limit above the 6 mole% in AgSbTe2. So with that, what we have done, we have measured the electrical transport at very low temperature of this compound, and when we have resistivity showing this kind of minima in the electronic transport at low temperature, and this minima for this pristine compound is a signature of electronic state localization due to silver and antimony disordering in this compound. So where we get this indication? You can see there is a increase in the electrical resistivity at very low temperature. At that low temperature data can be fit with the root T dependence, which is nothing but the electron-electron interaction. And also we have weak localization in this compound. And this side the electrical resistivity increases due to the breaking of coherence by electron-phonon scattering slightly in a higher temperature. And Tm, actually that position of the Tm in the temperature scale decide how much extent of ordering or disordering we have in this compound. So you can see the Tm moves to lower temperature as soon as we put cadmium 6 mole% in this compound. So that tells that cadmium doping actually partially ordering silver and antimony in this compound. So the localization regime has actually shifted to a lower temperature. So then we have measured basically the Seebeck coefficient, and you can see the Seebeck coefficient, the blue curve, which is a pristine compound, shows a bump at exactly same temperature where we see the resistivity minima. And this bump is nothing but due to the distortion of electronic state, which is proposed by Neville Mott for the long time back by this equation. S is directly proportional to the first derivative of the density of states. But as soon as we dope cadmium, this bump goes away. So that's basically, we are moving from the localized regime to the delocalized regime, because we are creating partially ordering of silver and antimony by little bit of cadmium doping. So that is the first indication we have from the low temperature electrical resistivity and the Seebeck coefficient data. So let's see what we can do next. So we have collaborated with our theoretician colleague Umesh Wagmane, and he has calculated the formation energy. And you can see the ordered AGSB T2 structure having more stable compared to the first nearest neighbor and second nearest neighbor disordered structure, which has been proposed by Mohanty around 2007 in his PRL. But what is new here? When we created this first nearest neighbor and second nearest neighbor disordered structure and put cadmium in it, it showed that actually cadmium removes the disordered antimony from this structure. So that means cadmium likes to go to the disordered antimony position, and that tells us basically cadmium is 2+, antimony is +3. So we'll have extra hole doping in this solid, which will move the Fermi level from also the mobility edge. So that will have another handle of optimizing the electronic structure. So with that, we have calculated the electronic structure for ordered AGSB T2, and you can see it has a flat valence band, which is very good for p-type Seebeck coefficient, and a dispersive conduction band, and this is a semi-metallic compound, as I showed basically in the cartoon in the initial slides. And you can see when we make the disordering of AG and SB by first or second nearest neighbor disordering, there is a localized states coming at the Fermi level. So that's what we are actually seeing from the low temperature electrical resistivity and Seebeck coefficient measurement. And if we visualize that, this is nothing but the tellurium p orbital, and that sits at the Fermi level. So this is no good for actually thermoelectric, because the localized electronic structure can actually localize, make the material insulator from metal at very low temperature. So, so this is the localized states, which is the tellurium p states. But as soon as I dope cadmium, this states vanishes. So that's what we actually observe. And cadmium actually pushes the Fermi level down in the valence band. So that also moves from localized states. So this is also an important thing while doping cadmium in this compound. So then what we have done, we actually try to estimate the whole electron and hole concentration, as well as the mobility of electron and hole. As this is a semi-metallic compound, it's very difficult to do a simple Hall measurement to find it out those. So we have to do basically Hall measurement and the magnetoresistance measurement. And by fitting this formula, actually we can estimate both this concentration. So you can see here, like this is the very busy plot. I'll simplify in a minute. So this is the carrier concentration of pristine AGSB T2. This is the whole concentration. The cadmium doping actually doubles the whole concentration. It takes to 10 to the power 19, higher 10 to the power 19. But the mobility also we see also similar mobility after cadmium doping. So that tells that although there is a decrease, but we could expect a huge decrease in the mobility because of the huge increase in the p-type carrier concentration. But we don't see that much decrease, although it is similar at lower temperature. So that also tells that there would be a chance of delocalization of the electronic structure. So then like we ask ourselves, can we see actually by eye this atomic ordering and disordering? So what we have done very, very high resolution scanning transmission electron microscope in the setup of head-up, and we actually this is a pristine compound, and there is no ordering of atom. And you can see that from the electron diffraction, there is a fundamental spots for sodium chloride structure. But as soon as I dope 6 mole%, you can see there is fluctuation of the intensity at the nanoscale, and this fluctuation of the intensity at the nanoscale like 2 to 4 nanometer is due to the ordering of silver and antimony in this compound after the cadmium doping. And the electron diffraction, it will be much more clear. You can see there is a halfway spot, weak spot. So that comes from the cell doubling. So cell doubling happens, and the compound orders, and the ordering dimension are the size of 2 to 4 nanometer. So we are fortunate this compound has the phonon mean free path, which are in the range of 2 to 6 nanometers. So we are hitting the sweet spot. So that basically this nanostructure are not only forms delocalizing the electronic states, moving the mobility edge from the Fermi level, but also it will scatter the acoustic phonon tremendously. So we have two handle as soon as we have actually created this kind of nanostructure of this compound. So then what we have done, we have keep on doing more microscopy study, and you can see there is a nanoscale superstructure spot. That is due to basically the nanostructure formation of the size of 2 to 4 nanometer, and we have done also dark field microscopy, because once this ordering happens or partial ordering happens, it may form nearly degenerate structure, because the ordering can happen in different crystallographic direction, and the lattice parameter will be similar for this ordered phase, and also energy could be similar. So they will stabilize in the matrix, and what will happen actually, that will gives a lot of strain in the lattice, and those strains are extremely good for scattering the acoustic phonon. So that's why we see this strain ripples as well as from inverse fast Fourier transform images. So we see this strain ripple, and that is formation of due to this nanostructure. So then what we have done, we have measured the low temperature heat capacity, and this low temperature of the heat capacity generally follows the Debye law. But you can see in this particular compound, this low temperature heat capacity Cp by T versus T square plot at low temperature could not be fitted by simple Debye law. So we have to invoke the Einstein modes, which are basically the localized optical phonon modes. And once we included in this our equation, actually, Debye-Einstein model could easily explain this heat capacity. And the energy of this Einstein localized phonon modes are extremely low in this compound. So that tells that basically there is a plenty of low energy optical phonon in this compound, which can also scatter the acoustic phonon by avoided crossing mechanism. And when we have plotted Cp by T cube versus T, which shows a boson peak, which is fascinating, and this kind of boson peak actually observed in disordered glasses. So this compound has all the potential to have low thermal conductivity because of nanostructures by atomic ordering, which are in the size of the phonon mean prepar, 2 to 4 nanometer, and also a lot of strain, and also plenty of low energy optical phonon modes. So let's see what we have done. So we have measured the thermal conductivity, both total and the lattice thermal conductivity, and we see there is a tremendous drop in the lattice thermal conductivity in this compound, which is around 0.2 watt per meter Kelvin. So this, which is almost to the glass limit in a crystalline solid. And with this, what we have done, we have measured the electrical conductivity. You can see the electrical conductivity jumps as soon as I dope cadmium in this compound, and that happens due to the enhancement of the electronic transport by partial atomic ordering, because it delocalizes the electronic states. The Seebeck coefficient remains high in this compound, even the carrier concentration doubles by cadmium doping, because it has a flat, nearly flat valence band. At the same time, valence band values are also in the similar energy. So, and we have a tremendous drop in the lattice thermal conductivity due to the phonon, acoustic phonon scattering by nanostructure, as well as basically strain and large density of low energy optical phonons. So we get a ZT of around 1.4, around 1.5 at room temperature, and mid temperature it goes up to 2.6, and which is one of the highest in this mid temperature range when we compare with all the state of art. So we have also not only published this work, and we have also patented and protected this. And this is also, I should mention, this is a P-type material. So what next? So what we can do next in this AGSBT2? So what we have done, as a chemist, we know well periodic table, and you can see. So cadmium is 95 picometer, which is the average size of silver and antimony. So can we try mercury doping, which is also similar size? And actually, we have started with zinc. Zinc didn't work. So we get a ZT of around 1.8 with zinc doping. So that we published first. Then we came to cadmium doping in this compound. And mercury, which is 102 picometer, mercury 2+. So as soon as we dope mercury in this compound, there is a expansion of the lattice parameter. A slight, and then mercury goes up to 4 mole%, which is the solid solution limit. Cadmium goes up to 6 mole%. That tells also we are doping right way this mercury and cadmium in this compound. So then the Umesh calculated the formation energy, and exactly also it says mercury also removes the disordered antimony from the crystallographic sodium side. So then we have gone ahead and tried to understand the chemical bonding in this compound. So you can see this is the electronic structure of this AGSBT2. And electronic structure valence band is generally formed by, surprisingly, tellurium p orbital and the interaction of 5s2 lone pair of antimony. So that also hints, basically, antimony lone pair is locally stereochemically active. And we have evidence from synchrotron X-ray PDF data. I'm not going in that direction today. So locally, the antimony expresses the lone pair and distorts the crystal structure. But globally, the structure is basically rock salt structure. So I'm not going to that. But more importantly, it forms an antibonding band by simple like Kohov type calculation. This is crystal orbital Hamiltonian population type calculation. And this antibonding orbital actually forms the valence band. So if we fill up electron in the antibonding band, the structure becomes destabilized, right? So probably that's why AgSbT2 always forms with little bit of impurity of Ag2T and other thing. So if we move the Fermi level from the valence band top to down, basically we can stabilize the structure. So that's why cadmium and mercury doping actually stabilizes the AgSbT2. So then we have gone ahead and try to understand more in a chemical bonding of this compound. So that was like one kind of bonding which is metavalent bonding proposed by Matthias Wittig in around 2019. So I'm citing his later paper, where the chemical bonding is different than actually covalent and metallic bonding. So for covalent, and it has been shown by electron shared by electron transferred map. And you can see that for 2 electron shared, the strongest covalent bond is diamond, whereas the electron transferred, it is the ionic compound, where the electrons are shared. But surprisingly, this AgSbT2 or other important thermoelectric solid sits where the electron shared is 1. So these are called metavalent bonding, because antimony and tellurium has basically 6 electrons, but they are forming octahedral coordination. So that means we are short of 6 electrons. So that's why the 1 electron is shared. So they termed it is the metavalent bonding. And the metavalent bonding, what we understood from our electronic and the thermal transport measurement, these are extremely good for thermoelectric, because they have defined the descriptor. So this is, it has moderate electrical conductivity and high optical dielectric constant, which is not there in the metal. High effective coordination, as I just explained, which is not there in the covalent. Electron transfer is low, which is not there in the ionic. And it has high bond effective charge. And this bond effective charge actually are a good indicator for anharmonicity in this compound or any metavalent compound. And this anharmonicity is important to have low thermal conductivity. So by doing this, basically by ordering or disordering of atom in the partial scale, actually one can tune this metavalency in this compound. So that's what we did in mercury doped compound. So, and as soon as we dope mercury, basically we see this nanostructure, and which are formed by silver and antimony ordering. And you can see this halfway superstructure or like cell doubling spots. I'm not going to the details. So then we have, so we get a ZT of around, we get a ZT of around 2.4 with mercury doping. That actually supports what we have done with cadmium. So now, last few minutes, basically I'm going to talk, and we have also created the device which will have, which have the efficiency of around close to 8.5%. This is a preliminary device which is very, very good compared to the state-of-art thermoelectric devices in the market. So now, while doing this work, we understood the challenge, because we are moving this Fermi level down all the time by putting +2 dopant at the +3 site. So that partially actually masks the effect of moving mobility edge towards the band edge, basically. So can we keep this Fermi level at the same place and see the only effect of movement of this mobility edge? So that's the challenge remained after doing the work. And then that means we have to do isovalent doping. And isovalent elements could be ytterbium. We found it from the studying the radiuses and all. And it was that means ytterbium probably will do the same thing cadmium or mercury does. It will partially order the like atom and forms in the nanoscale superstructure. But those nanoscale superstructure or nanoscale structure will see phonon, scatter phonon, but it will help to pass through the electron and hole. So that's the idea we have. So can we have basically an ideal thermoelectric system, which is nothing but phonon glass electron crystal system? The phonon will behave like a glass, charge carrier will behave like a crystal or metal in this compound. So that's the idea we have. So in order to do that, what we have done, we have doped ytterbium, and you can see the carrier concentration, hole concentration is fixed throughout the temperature we measured, because this is isovalent doping, it will not change. But there is a 2-order increase in the mobility. So there is a direct signature, and this is measured from 2 Kelvin to or almost like 550 or 575 Kelvin. So that tells that, so the partial ordering of atom actually delocalizes the electronic state. So this is a direct proof of that. And this is a thermal conductivity at low temperature for GSB-T2. But as soon as we dope ytterbium, it's become glass-like, because the low temperature thermal conductivity should follow TQ law, which is nothing but the Debye law. But this is a deviation from TQ, which is T squared. So, and we have a plateau. So this Umklapp peak also suppresses. We have glass-like thermal conductivity, but crystal-like electrical conductivity. So this is one of the, could be a good system for thermoelectric. And how we did it, actually? So basically, we have to have design a material where gap between the mean free path of charge carrier and phonon should come in picture. So as soon as we dope ytterbium, there is an enhancement of the mean free path of the hole, but the phonon mean free path decreases. So we see a glass-like thermal conductivity, but crystal-like electronic transport. And we could see a thermal conductivity around 0.2 watt per meter Kelvin at higher temperature. And with that, actually, we see all this weak localization phenomena. I'm not going to the details in this case. And what we see at low temperature magnetoresistance, at very low temperature, 2 Kelvin, we see this kind of a cusp-like feature. So that tells that quantum diffusive type transport, which is nothing but the weak anti-localization. And also, we see root 2 dependence, which tells that basically this is coming from the electron interaction. So this has both diffusive and quantum diffusive transport is happening at the low temperature. And then we get a ZT of around 2.4 also in this 4% ytterbium dope compound, and we get a good device efficiency. So we are learning device currently of doing thermoelectric. So I don't have much time, so I'll finish it here. I'll skip the last work. So what we have done, I'll come to the conclusion. Yeah. So before coming to the conclusion, I'll tell one thing, because as I talked about introduction, like waste heat recovery can be done in power plants, right? And then we are working with Tata Steel, which is one of the famous steel company in the world. So they actually quench the blast furnaces, which melts the iron ore by steams. And those steam pipes actually runs around throughout their steel power plants. So they given us the challenge. The target temperature is around 110 degrees centigrade, and the current heat loss is around this much kilowatts. So can we convert this waste heat to electricity? So over the years, we worked with them and created this P-type and N-type thermoelectric material near the room temperature. Those are basically based on bismuth, antimony, tellurium, and selenium. And we have also patented our work. We have a joint patent, and we have scaled up the material. We have made multi-leg devices, and we showed actually putting them there by collaboration with Tata Steel, JNCSR, and ARCI. We showed a 1 kilowatt generator can be built in the steel power plant by our material and prototype. So with this, I come to the conclusion. So we have measured extremely high thermoelectric figure of merit in AGSB-T2 systems by partially ordering the atom. So partially ordering the atom actually delocalizes the electronic states, and partial ordering can create the nanostructure, which are the size of the mean free path of the acoustic phonon in those compounds. And while doing this, because I want to tell one general thing, because in thermoelectric community, people thought till now they will solve the problem by disordering the atom, because there is a significant amount of disorder is there in the all optimized thermoelectric material. So we actually gone in other direction and told, okay, disordering is good, but not that good. If we can put little bit of ordering, that can actually solve many problems we can tune actually electrical transport and phonon transport together if we have actually can create partial ordering in the states. So our idea is general, we believe, and that can be applied in many thermoelectric material. With this, I acknowledge my group. So these are the initial group, and this is the current group, and I have significant amount of excellent collaborators, and the red ones are basically the contributed in this work, and generous funding from Department of Science and Technology, SCRB India, of course, Sekshakal Laboratory in JNCSR, and a new chemistry unit, my own institute, Tata Steel, and recently I have a fund from Quantum Technology Foundation, I have. So with this, I'd be happy to answer all the questions. Thank you all. Sure, so one. Yeah.
We have short questions. Time's just up. I'm sure the
Yeah.
question is put up.
Excellent talk, Kanishka. I just wonder, a quick question. Many of the material, or maybe some of them, might undergo phase transition at
Right, yeah.
temperature. So, can you comment what happened at the
Sure.
moment when?
So the material I have discussed today, those are rock salt phase, which is one of the highest symmetry phase. So that cannot go generally for a phase transition. But there are material which are lower symmetry phase. If you heat it, it will go to the higher symmetry phase. That is a phase transition. But phase transition, it may not be a good thing for thermoelectric because always it will come with a hysteresis because of first order phase transition generally, right? And those hysteresis are actually can be bad for thermoelectric devices that can crack the thermoelectric device. But some of the material which shows superionic type of phase transition, those are fundamentally very good for thermoelectric because you can create kind of a liquid-like lattice which can kill the transverse acoustic phonon very much. So some of the work has been done in that direction. We also did it. Yeah.
You would like to avoid phase transition temperature range in which we want.
Right. Yeah.
All right. Thank you.
Yeah.
Maybe we'll extend a little more. If there's another urgent question, we can take a short one. Well, then maybe we can carry on the discussion
Thank
at
you.
the tea
Yeah.
time. Let's thank Kanishka for a wonderful talk.